5 volt or something. If it is not on a 0 to 5 volt or something, we need to improve it, and that is what in amplifying electronics it is used. If you look into the temperature sensors like thermocouples, whenever we are having a temperature change, this is the temperature on one axis and millivolt change in the voltage it happens. So this is 0 degree, maybe 1000 degree, okay? So during this 0 to 1000 degree, it is going to show me hardly 50 millivolt change, which is very small enough, which our electronic system cannot understand quite easily. So for that purpose, this 50 millivolt to be amplified means I have to have here in input of the amplifier, there will be a 0 to 50 millivolt change, and amplifying electronics will convert now 0 to 5 volt or maybe 0 to 10 volt kind of things. So these all comes under the analog category of the sensors. Analog means any value in between I can trace it out, or also you can say it follows on a decimal numbering system. So that is kind of thing. Once we got this voltage, higher voltage, why we have to improve? Because we will get more accuracy, we will get a better measurement idea, so many things we can get it. So that's the reason we need to amplify it. Once we amplify this analog signal, and here it is in a microcontroller, which follows a language. So I will tell you one simple example. If you go to some other country like China or somewhere, that language we don't know it. So what we do it, we translate that information into our own language. Maybe we are using English as a medium for it. So that is what the way this microcontroller, here it is your language is somewhere decimal number, or you can say it is an analog language, and here it is in a digital language. So that is what it is to be converted. So that's what analog to digital converter. Analog to digital converter is to be mounted at this, and that is nothing but a part of your data acquisition system. So once we got this DACs for each and every sensors, I may have multiple ports on it, maybe 1, 2, 3 multiple ports, and I'm going to have a temperature on one port, then displacement on another port, humidity on third port, like this, maybe a 10, 15, 20, 30, like this. You can have a bigger data acquisition systems also. So this will, each and every port will have one ADC attached to it. And that ADC converts that information into a binary language, that is 0, 1, 0, 0 something. And that is bit of accuracy you are looking for it. And that is the way it works. And then it goes to a microcontroller, which understands your binary language. And this binary language, in this we may be keeping some kind of a logic for it. So that logic is called as a control system. Means, just I will tell you one example. If you are increasing the temperature of water, and you don't want to go beyond some 100 degrees Celsius or maybe 50 degrees Celsius or something. So after 50 degrees Celsius, I want to switch off the heater. So what we can do it, we can generate a signal for the actuator, and that is possible. That is what in a logic it is called as a control system. That logic will be much more complicated if you use multiple sensors, multiple systems, or maybe kind of a robotic system kind of thing. More and more complicated, and it is more related to, more oriented toward mathematical calculations. Once we generate some logic, and this also have some binary language, that is whatever the output it generates, it is in a binary in terms of binary numbers or digital numbers. And this digital number, and your actuator understands your analog. You can just take a simple example of motor. And if I want to change the speed of the motor, what I have to do, I have to change the speed, means I have to change the voltage. And that voltage will be changed with respect to time. Voltage may be smoothly varying like this. I'm not going to change it with a step like this. So if I'm going to change the steps, then it is called as a decimal numbering. And if I'm going to change it smoothly, then it is called as an analog kind of thing. So obviously this binary information again need to convert into analog systems. analog. That's what this here comes upon. Here it is a digital number. Here it is an analog number. That is to be converted. Then it is reverse of ADC. It is called as a DAC, digital to analog converter. Then digital to analog converter will now generate a signal that is 0 to 5 volt, maybe 0 to 10 volt, sometimes minus 10 to 10 volt, like this. So depends on configuration of your microcontroller kind of thing. Darwaza band kar. Oi. Then this voltage is not sufficient to drive your motor. Okay. So that's what we need to have some power amplification. So this voltage, whatever signal generated by microcontroller, it is hardly 50 milliwatt of power, and your motor needs 1 HP or more than that, 1 HP, maybe 10 HP, something. So obviously this power will not sufficient to drive this actuator. So in that case, what is to be done? Obviously, I need to go for one more amplification, and there will be a power amplifier. This is what a power supply, which supplies this, and according to 0 to 5 volt, I may be getting here 2.5 volt, and here I want 0 to 230 volt as an output for 0 to 5 volt. So it will map it. Map it means it will half of it. That is, it will give, if it is 2.5 volt it is generating, it will now generate 115 volt as an output. Like this is nothing but an amplifying electronics. And this amplifying electronics will now create an give the energy to the actuator in terms of a voltage, maybe a current kind of thing, and this actuator will now drive your mechanical system. It is like this. This is what it involves so many things into this. What it involves, it is first is mechanical system. This is what a mechanical system. Second, it involves sensors, which convert in
presentation. Yeah. Your presentation somewhat that is not showing here.
Okay. Maybe some issues will be there. I think just check. I will check it out.
You need to present.
Once again, I will. Somewhere I got. Once again, I will share it. I think.
Okay.
Can you see my screen?
No, sir.
No. Okay. Just what I will do, I'll just once again log out and once again log in, so that will serve the purpose.
Sir, sharing right now.
Sir, you're starting present sharing. It started, sir.
It started.
Just a minute. Okay. It is.
It shows it's after some time.
Yeah. Maybe. Let me. I refreshed it, so it is asking me to join because I joined for a mic through the mobile, and I joined for a screen from the laptop. It is like this.
Okay.
So that is what the thing. So that's what you can see my two logins in there. My mic is having some problem, I think. Okay. So let me. You can allow me for, okay, I have a presentation. I'll full screen, your entire screen.
Sir, your screen is visible.
Yeah, can you see my screen now?
Yes.
Yeah, meanwhile, just let me do one thing. And, okay. So we'll start then, okay. Can you see the screen now?
Yes, sir.
Presentation? Yeah.
Yes, sir.
Yeah, yes.
Yeah. Now we had a discussion just now. Let me switch off the camera. I think camera is having an so there is an issue in the camera. Yeah, I think it is okay.
Yes, sir.
Is that visible now?
Yes, sir. Yes, sir.
Yeah. So here you can just look at one thing into this, that we have seen a mechanical system here. This is a mechanical system. This is a sensor. It is again electronics part. Again electronics part. So this is what called as a digital signal processing, or we can say it is in a microcontroller part, or we can say it is in a computer part, microcontrollers. And then again amplifying the device. Then here it is an electrical to mechanical change. That is what we are going to do it. Here a mechanical to electrical you are going to change. Here it is a electrical to mechanical. So that's what we here in this mechatronics domain. We are clubbing together so many things at a time. So that's what it is called as a mechatronics. It is an integration. It is a marriage of so many fields into a single unit. And so that's what it is called as a mechatronic system. So we'll take up a few examples. These are the few examples I have taken for you. One is antenna control system, then unmanned free-swimming vehicle, then space shuttle or pitch control system. Also, we'll discuss about human eye control, how that control works, and last part I'm going to take an optical drive. So if you look into the antenna, so this you can just look at this picture. So this is what on a dish you want to rotate it as per your requirement. So your dish may be at initially at 30 degree. You want to move it to the 30, 35 or 40 degree like this. So that is what the way you want to have a control on it. So here for that purpose to control this is what on a potentiometer which measures the actual position of the antenna. So that is what it is, nothing but a sensor, actual sensor, it measures it, and which will initially take a signal in theta as an input to this, and output it is generating voltage as an output. That is what a potentiometer. Potentiometer is a simple device which is similar to our volume button in the all radios or something. So that is when you are rotating it, it will equivalently convert or linearly it will convert in terms of voltage. That is what a potentiometer does. So here in this wire you will get a voltage as a signal. So this wire voltage will go to the differential amplifier. So here I got a voltage as an actual. This is another potentiometer where I want to set up an angle. That is what. So this differential means it is taking a difference of your desired voltage and actual voltage. So that is nothing but a signal. We need it to change, create a change in the position of the antenna. So that is what it is done by a differential amplifier. Means it is input is taking as a difference of these two, because both the wires are going inside. There is a device which will take a difference of it, and it will now have some amplifier or some electronic device in this, and that will convert a larger voltage to the motor. And motor is again voltage signal, and that motor will now generate a torque onto this, and this torque and also speed means ultimately power. I can say it is a mechanical power it will convert, and then it will start to drive the gears, and gear will now start rotating the antenna. So that is what the way it involves. This is a very simple mechatronic system. There is a mechanical system, gear drive antenna or something. There is an electronic system. These are electrical systems. This is again electronic system, and that is nothing but a connection of it. So when you look into the analysis of it, so individual system have its own input and output characteristics, and that is what it is called as a transfer function. So if I take a potentiometer, so it will theta as an input it will take, and voltage it will change. Means if I plot on one axis theta and other axis voltage output, so I may get this curve, and whatever the slope of this curve is called as a transfer function of it. So I'm going to tell you very simple case, but in case of transfer function, it will not be so simple the way I'm going to tell you. So it becomes too much complicated as the dynamics, means as speed of my input is going to change, output also changes, and there is a possibility of resonance, there is a possibility of matching the natural frequencies in the system, and it will become too much complicated. But simple case you can consider. So theta, it's a ratio of transfer function is nothing but a ratio of your output. So I can say it is a voltage and to the input. So that is theta. So when you are dealing with a static kind of a system, it's simply I can say it is an output to input. When you are dealing with a dynamic system, then you are taking a Laplace of it. Laplace is the unit, or it is a transformation or mathematical tool which is mostly used to handle the dynamic conditions of the system, to solve the dynamics of the problems. So typically Laplace transformation is used for converting differential equation into a simple algebraic equation, solve at that equation, and then again inverse it. That is what the way this Laplace will be used. So for that purpose, individual system have some input-output characteristics. So similarly, you can have a potentiometer as a one transfer function, motor having a one in transfer function, which will take a voltage input to the motor, and output is torque. So I can have a relation between T and V in. Here differential amplifier, I will have two input, one is VD and another VA, and output is my V input. Mechanical system, torque will be there and theta will be an output. So these individual systems have an input-output characteristics, and these input-output characteristics are typically represented in terms of blocks here. So here it is the input is the angle, then voltage out. Relation, and that is what a Laplace can be used here. So that is what the way it is represented a single system. The behavior of entire antenna is nothing but the behavior of individual components. Similarly, if you create a big project and you have maybe 15 or 20 people are working together, and the success of the project depends on individuals' performance. This system also works on the same non-linear system, I can say, also works in the same fashion. So this is what this potentiometer. Then power amplifier will have another performance parameter, performance characteristic. Plant, motor, gear, head, and everything will have another performance parameter. Potentiometer, another potentiometer will have a third performance characteristics. And ultimately, you want angular input, whichever the input you are going to give it at this location, and what is the output you are looking at this. So this relation you want it, because these two are connected to so many components till the end of this. And finally, these two are most important, and control system plays a very important role how to deal with this individual components. So that's what manager is most important person in the most of the organization or in handling a big project. So here you can see an input and output connections of the individual subsystems. Okay. So you can now give numbers for it, performance parameter maybe in terms of an equation or something. So here I can have an input potentiometer, then preamplifier, then power amplifier equation, then motor gear equation, then again potentiometer equation. So now I can combine this. Ultimately, what I want is, I want a relation between this theta and this theta. So that is the most important for us. Purpose, these all to be clubbed into a single block. So that's what we do it at the block diagram reduction kind of thing in all control systems. So we can combine, we can follow certain rules that can be taught into a separate class of mechatronics. So this is what it is combined, and finally you will get only one single equation in which you will get one k as a single parameter. So that is what a control parameter I can say. Rest of the parameters are okay because already it is fixed. Motor gear, we are not going to change the dimension of those during operation. It will be the same for everywhere. So every time, and this k you may change. You can have an authority to change this k only during real-time operation. So if I change the k, if I put upon a lower value of the k or lower value of the gain, I can say it is a gain for simplification purpose. So this k will, as I go on increasing the k value, what it happens, it will increase the response. It will make the system more and more faster. So that we'll see it into PID control part of it. Okay. So this is what the way a typical system should be divided into a small system, and look at the individual systems separately. So that is what we can do it. And these separate systems performance, individual systems performance, when they brought together, that will create a big performance and big output, and that is what analysis we can do it. That is, for that purpose there are different techniques. One, I can say it is in a block diagram reduction, another is a graph theory. So many techniques are there. So you can just signal processing, signal graphs, so many graphs are there. Okay. So here one more example I will just highlight here. And so here, this is submersible vehicle. Submersible vehicle means you are taking it to the water, in the sea water or somewhere, and you want to do some operations out there. So when you are taking that particular vehicle into the sea water, so it has to move down, it has to move up, so many operations it has to do. It should swim like a fish. So for that purpose, you need to control the depth of the vehicle. That is one thing. And also you need to change the orientation, deflection kind of thing. We can do it. So when you want to change the depth of the vehicle, okay, so how we are going to do it? During forward motion, what are the surface of the vehicle should be deflected such that it will further nodes of this particular vehicle will go down and it will start traversing in that. If I have to change the angle of it. So that is possible by just look at this picture. This is submersible vehicle. So this submersible vehicle, when I am going to rotate in this fashion, it will go in downward direction like this. If I am going to rotate this within a pitch axis in upward direction, or it will move into the upward direction. So to control this, there are certain system actuators are mounted, then there will be sensors on it, what is its orientation, so many things. So this can be divided into a small blocks. So here it is in a heading gain is there, then radar actuator model is there, then vehicle dynamics model is there, then 1 by S is nothing but an integration of this. This is nothing but a rate, velocity it is going to determine. This is what an angular position it is going to tell you. So this is what all individual systems, and when ultimately you are going to connect this with this output, and for that this connection we have nothing but this is 1, 2, 3, all these blocks are working together, and that is nothing but a way you are going to design your system. Once you design, then you are looking for changing the design of the system by changing this parameter, that is the gain parameter. And this gain may be in a card as in a control system. Maybe this gain is having only one single number, may 1, 2, something. This K may be having some function of some time or something, or function of some position, something. So this is called as a control law of your system. What is the way it behaves? What should be the behavior? And that is what decided by these laws. Then another one is the space shuttle pitch control. You want to change the position of it. The similar fashion, then it was happened in this another system. The same way we can work it out here also. So there are multiple blocks in it. So there is a commanded pitch, Then there will be a gain for it. This is one gain. This is my second gain. These two parameters now. Maybe your control system may have multiple such things. Then there is a controller shutter dynamics transfer function. There is an accelerometer. Then the gyroscope, that is velocity, it will determine pitch rate, I can say. Then this is what a position or inertial measuring in it. So all these will work together and it will give a performance. Just one thing, one most important example which we daily use it, that is our human eye. How it works. So whenever you look at any picture or any information through our vision system, so that is what here it is an object position we got it. Then this information will send to the brain through your nervous system. So these are the nerves through which it will collect the information. And there will be a certain delay. Just keep in mind, in sensor also there will be a delay all the time. Whichever sensor you are using, maybe in any very high fast or any sensor, there will be a delay because that information needs to be transferred from one place to another place. So that is what it will reach to the brain. Once it reaches to the brain, then brain will now start working. It will start analyzing the image. So that image will be analyzed, and based on that analysis of the image, this brain will now generate some signal. So maybe that particular image is happy, sad or something. Based on that, your eyes muscles, here there are muscles are mounted at this, and these are the muscles in fact. These muscles will now start contracting or reflecting. That is what it happens, and that signal is given to the muscles, and this muscle will now generate a signal to the eye, and it will change the position of the eye. So that is what it happens, and this is what the human eye movement control system. So there is one more interesting example, that is optical disk drive. So we used it long back. So nowadays this technology is again not in use mostly, but a few people use it. So in optical disk drive, so there will be tracks mounted on it. These are the tracks through which information is written. So that track is nothing but so if you collect it and you want to see it, how the information is written. So this is what the way it written the information. So this indicates 0 position and this indicates 1 position. This is 0, this is 1 position. Means whenever there is an upper part, and then it will, so top land, I can say it here, it is in a top land and this is a bottom land. So top land indicates 1 and bottom land indicates 0. So for that purpose, there is an optical system mounted on it. So this is what an optical system. So this will generate a laser beam. Okay, so this is what a laser diode. This laser diode will generate a beam, and this beam will be divided into 2 parts. One is used for referencing purpose. This is what a referencing purpose. Another beam, this is what it is called as a beam splitter. This beam splitter will divide the beam. This may be 100% intensity. Here will be a 50% intensity, and here it is going to be a 50% intensity. So this will be go through the mirrors and something through the lens, and it will concentrate on this particular point, maybe laser coming at this location. So then beam will get reflect back, okay, and it will start flowing back into this direction, okay, and then it will directly come and hit to this photodetector, and this photodetector is typically a quadrature type photodetector. Means I have 4 quadrants in it. So laser beam will be now looking at this. So based on this intensity of the laser beam, whether it is a focus, deep focus or something, so this will now reflect certain intensity, and that intensity is going to generate a signal either 0 or 1. Understand? So that focusing should be all the time perfect enough. So for that purpose, this is what a mechanism. You can just open up a CD drive. You can just look at the complicated parts and this, and you can see it. So this is one way it does. But most of the time, you need to focus the laser beam perfectly onto this. Your beam may be focusing at this location is not allowed. So for that purpose, there will be 3 tracks into this. This is nothing but a one data track, I can say, and this is another track which is typically used for focusing purpose. So in this case, laser beam will come here, and there will be some device that is what it is called as a beam splitter, or it will slit type of an experiment you have done it. So then it will generate 3 beams onto this. This is one beam, and this is my second beam, and this is my third beam. These 3 beams will get back reflected from this surface back to photodetector, and it will look onto the photodetector like this. If it is perfectly positioned, these quadrants will be used to track the track. That is whatever the path of the data written onto this. It will be controlled by these 2 another beams, and information will be processed through this. Processed from this middle track, and these other 2 tracks are to control the position of the laser beam. This is what controlled using there will be 2 small actuators. One is used for focusing purpose, another is used for tracking purpose, means this is what position I need to make it, and another one is that it is going to continuously rotate with maybe 3000 RPM or something, so means it has to continuously. This is all fixed part. Only the thing is that lens and laser beam is going to move up and down and sideways. That is what it happens. So this all involves so much of the control, complicated systems. Complicated means I have to have control on laser, I have to have a control on the speed of my disk, and then I have to have a control of focus of this. This is the focusing. I have to track also. This is a tracking control also. So many things are involved. So that is what it happens, and for that purpose it knows mechanical motion you are going to control, an optical information, and all this. So this is what a typical picture of the CD drive. This is what a head of this, and this is completely called as a head of your lens, and here you are going to mount your CD drive, and here it is in a lens of it. This is what on a lens, and how the information is processed. This is what on a laser beam is shined onto this surface. This is the land, and then this is it. This reflect on a. Here you can just look at, here it is whenever there is a small change, so it is representing 1 like this, and rest of the information is considered to be a 0, and here it is again changing, then it is represented as a 1. So this is what it is coded in 0101, and then this coding is further converted into your own language by using a digital, that binary to decimal numbers, and then it is converted into your own whatever the signals coming on the screen or kind of things. And this is what a typical picture of this entire optical disk drive. Here it is a laser diode, then grating, or I can say it is a laser speed splitter, then there is a beam splitter, then here it is a photodiode, then disk, and here it is in a mechanism which controls focusing as well as tracking. Here it is in a voice coil. It is called as a voice coil because it is such type of mechanism used in all the speakers. That's the reason it is called as a voice coil. Okay. So once we got this done, these are the typical, whenever we are designing in a mechatronics system, there are steps through which we need to work out. So first is physical system and specification. We need to define it. Then second step, we need to divide that entire system into small blocks, which we done it in last few examples. Then we need to create a transfer functions for it, transform physical system into kind of a schematic, or you can represent in terms of an equations, or so many things you can do it. Once we got this entire block diagram, which we created in step 3, should be brought into a single block diagram. And for that purpose, you can use a block reduction technique, signal flow diagram technique, or state space representation. Any of the technique you can use it for analysis purpose. And then multiple blocks to be reduced, then single block, and we need to create a closed loop type of system. Closed loop means you are taking a feedback, and based on that feedback, you are going to take an action. And that is what the kind of a system is called as a closed loop system. And then analyze and do this. Then, so this is what the way this entire mechatronics system works. I'll give you a brief idea about individual components. We have seen sensors, data acquisition systems, and microcontroller. I'm going to give a brief idea about it. So what is meant by sensor? Sensor is nothing but first of all, it will collect the information in some sense. Like if I'm going to touch to a certain surface, it will generate a force onto my skin, and that information of force on the screen is converted in terms of electrical signal to my brain. So it passes through so many stages, and that is what it is called as a sensor. So if you take a simple example of RTD, RTD means resistance temperature detector. Resistance temperature detector means if I am going to change the resistance of my temperature, I am going to change. Maybe 0 degree, maybe 100 degree, I am going to change it. So resistance of that particular material is going to change. So maybe if you look into some material where you increase the temperature, resistance decreases. Or some sensors, maybe as I increase the temperature, resistance increases. That is also possible. So this is what is called as a positive temperature coefficient. Okay. And this, sir, maybe it couldn't be audible.
Hello, sir.
हाँ सर ऐकू येते का ऍक्च्युली काय आलं परत लाईट गेली आता आमची चालू प्रॉब्लेम झाला बर
ठीक आहे
परत वाट बघू आपण एक 5 मिनिट ठीक आहे नाही ओके एक 5 मिनिट थांबा
सर तुमचा आवाज येतोय का कंटिन्यू आहे म्हणजे स्क्रीन विजिबल आहे आणि तुमचा आवाज पण येतोय ओके आय थिंक सर हॅज लेफ्ट we'll wait for 5 minutes.
Sure, sir. Hello.
हॅलो
हा सर
तुम्हाला व्हिडिओ पाठवला होता ना सरांनी
हा मीनवाइल आय विल
तोपर्यंत मीनवाइल तो प्ले करा
Good grammar and spelling are important, but if you
what does these two methods are? And that is nothing but my system model. I can say it is in a model of it, or we convert into Laplace transform. Yes. So with small blocks. Have different blocks. Here it is in one. This is the second system, subsystem. Have this gear, antenna, each and everything will become in a fourth system. Then fifth system like this. Multiple blocks. These blocks are interacting with each other, and that interaction is going to result a position of the antenna. So that is what it is done by block diagram representation. Here it is an angle as an input to the potentiometer. This is a desired angle I can have. And here it is a desired voltage I will get it. Here it is in a summing junction. This is nothing but creating a difference of it. So here it is another potentiometer. Here theta is my input. Voltage is my output. So will result into V minus VA. Nothing but an error signal. And this
Bhigwan sir, voice break होता है.
So there is an issue in network. That's why this is problem.
otherwise, so it is called as a differential amplifier. And that differential amplifier will now do both the things. It will consider, take account of this error and also
Right now it is audible.
Voice is very low.
changing the function of the gears and so many things. And it is going to change.
Not audible.
So ultimately, this is my actual angle, and this is desired angle. Ultimately, what we want the relation between this one.
Okay, sir. We will wait a few minutes for them.
Okay.
Actually, in villages there is electricity problems are everywhere, so that's why this kind of problems are facing.
Yeah. Yes, we can understand.
Hello.
Sir,
येस सर. येतो पण थोडा
can
व्हॉइस
you hear
ब्रेक
me?
होतो सर.
हाँ सर. Actually, within 5 minutes, we can conclude the session, sir. Hello. Takade, sir.
हा यस सरांचं व्हॉइस ब्रेक होते.
हा सर, येस सर,
हो, हो.
कधीच
Yes,
लाईट
sir.
जात नाही. आज आमच्या इकडं लाईट कधीच
हा
जात नाही.
सर.
हॅलो.
हा नाही, इलेक्ट्रिसिटी प्रॉब्लेम नेटवर्क, त्यामुळे नेटवर्कला प्रॉब्लेम येतो. बरोबर आहे सर.
येस सर. येस. हॅलो.
हा सर, येतोय आवाज तुमचा.
येतोय आवाज.
हॅलो.
हॅलो.
हा येतोय सर. नाही पण आवाज हे होतोय, असं ब्रेक होतोय, कंटिन्यू येत नाही. हॅलो, आता येत नाही आवाज सर, येत नाही.
हॅलो सर. हॅलो.
हा ठीक आहे सर.
Deshmukh sir, we can conclude today because there is a lot of problem in electricity as well as in the voice connectivity. So we will try to organize another one session, one more session based on mechatronics, robotics, and automation. There is definitely no doubt about that. So first of all, wish you all and Dr. Suhas Deshmukh sir, wish you very happy Teachers Day, and thanks for giving a valuable time for us. Uh, uh, Thanks for giving a time slot for us, allow us a time slot for us. And I would like to thanks to Mr. Katare sir, HOD, Department of Mechanical Engineering, for giving a opportunity for organizing session. But because of some technical problem, we cannot complete our session. We cannot uh, complete that session. So sorry for all the audience for this technical reason. And thanks to our president Joel sir for allowing us for organizing such a wonderful webinar. Also thanks to our academic counselor Dr. Gauri sir and our
Hello.
director Dr. Kane sir. So I would like to say thanks to all participants and audience for your patience as well as for participating in our in this program. So because of this technical reason, we cannot complete this program. We will try to organize one more session on this. Once again, thank you very much. Thank you, sir.
Okay. Yeah, I personally thankful to Dr. Suhas Deshmukh sir, who has given us his valuable time, spared his time. But due to some technical problems, we cannot continue. But surely we'll organize the next section. Full guidance from Dr. Suhas sir. Thank you all for joining this session. Thank you very much. We can now we conclude. Okay. Thank you. Thank you all.
Thank you, sir.
Okay.